étale extension. So we just stopped short of defining étale extension. Can you define it?
Can I define étale extensions? Sure. Let's define étale algebra. An extension will be étale if it is étale as an algebra. So before that, we'll say diagonalizable algebra. So K is a field. Algebras are commutative, associative, unital. So diagonalizable algebra is A is diagonalizable if A and E is étale. So E is an algebra. If E, by that we mean for K, for L an extension field of K, is diagonalizable over L as an L algebra. So after I tensor with L, it becomes a product of copies of L. Yeah, this is an algebraic definition, and I defined separable algebras, right? Didn't I? Okay, I'll define separable algebra. So separable algebra is so S a K algebra again. Maybe I should have used a D because E for étale, D for diagonalizable, S for separable. Anyway, S a K algebra is separable. So these are definitions. If is reduced of, so here I mean for some, yeah, that's understood, but just to be clear, if is reduced for all L extensions of K. So what is clear is that diagonalizable So implies finite dimensional. Right, is isomorphic as K algebras, therefore as vector spaces. This implies et al. This says there exists an L for which it becomes diagonalizable. If it's diagonalizable over K itself. So you can take L to be K, that's obvious. And this implies separable, that's not hard to see. Now, just the proof of this very quickly is the following. So, we want to show that, so I take some et al. I want to show that for any extension this is reduced, right. Now, there exists an extension L for which this will split into this is diagonalizable over that. So I choose some, what should we call it, M. This is containing both F and L. Right. So, to show EF is so EF is contained in EM. Right, F is contained in M, therefore EF is contained in EM. If you wish, what are we using? Every vector space is flat. See, so what are we doing? We are tensoring this injection with E over K. So what's important here is that K is a field. Therefore, when I tensor an injection with a flat module, it stays flat. And every vector space is flat, so when I tensor it, it stays flat. That's why this is true. Okay. So I want to show this is reduced. Therefore, it's enough to show this is reduced because this is contained, right? So thus, so this is because E is flat, because K is a field. Okay. That's maybe a very roundabout way of saying it, but in any case, there it is. So, thus, to show EK or EF is reduced enough to show EM is reduced. Right? But what is EM? EM you can write as EL and then M, because I can tensor with L and then tensor with M. Okay. Now, when I tensor with L, this becomes L direct sum finitely many copies. I am a little loose about writing cross or direct sum or something. It's just a direct sum or product. Okay, let's write a product if you wish. Right? But that is the same as tensor commutes with direct sum. So that's same as and this is reduced, right, because it's a product of reduced algebras. So this is reduced. like I said, those notes that I have on my web page, if you want to, those have these definitions and more. Okay, in case you want to look at them. Is that all right for now, or if you want more, I can say more. But maybe I'll wait until, I mean, you can ask me more, and I'll be happy to say more. Okay. Now let's so for today, no matter where we end up, let's say right, we'll finish 4.2. Okay, whether or not I finish it in class. And next time we'll start with simple points. Okay. Okay. Now so let me put up the theorem for the main theorem for the case of fields. Right. So this is the theorem. So K is a field. So these are field extensions. Okay, let me use F because he keeps using F and I might lapse. Field extensions. And this is assumed to be finitely generated as a field. Okay, he does not say this at all. There is no, that's one thing about this book. There is no, important things and things that are just sidelights, highlights. There is no highlighting. Everything is, it's for you to see the perspective. Line after line, it's there, it's all there. It is important that it is finitely generated as a field. Okay, so that's a very, it's not a matter of just for the sake of keeping it simple or anything. It's important. So the first thing is that dimension. So we have seen this is the universal module of derivations. So this is an E module, right? So I can consider the dimension of that. Okay. Now is that finite? First let me ask you. Yes? Very good. What is a bound for the dimension? M. Why so? Right, indeed. So notice, again this is not remarked at all. So remark is that if I have a derivation, so I want a derivation D E F. This is my universal derivation, right? This is f of x1 to xn, xm. Notation is fixed. Now, f of course goes to 0, right? So f maps to 0 under right. Now I claim that this is determined by, so if I restrict it to say these elements may or may not be algebraic, right. This is the ring generated by x1 through xm inside this field, right. This image here determines this derivation because of the quotient rule. Once you know how it acts here, you are forced to act it by the quotient rule on rational functions here. This is not exactly maybe rational functions, but not all this may be algebraic. For example, if m equals 1 and this is algebraic, this is the same, right. But once you know the image here, it's determined here, right. And f goes to 0, and once I know the images of dx1 through dxm, I know everything else because by the Leibniz rule, right. If I have f a polynomial, then where are you forced to send it? You are forced to send it to f prime of x1 xm del right. If I wrote that correctly, this is where you will be forced to send f. So indeed, this dx1 through dxm, if I know the images of the xi's, that determines this derivation, right. Now moreover, as we saw, even over an algebra A, this is generated as an A module by the images of these things, right. Now this is determined by where this goes, right. Not just that, so once I am I saying that correctly? Well, see, I want to say that this as an E module is determined by the images of these, and indeed that from that it's clear that the dx1 through dxm form a spanning set for that vector space. Okay, so indeed this is at most m. Okay, so this is less than or equal to m, right, that we know. Okay. But the claim is this is actually less than or equal to, or sorry, greater than or equal to. So this is less, that's an aside. Okay, that's not. This is bigger than or equal to the transcendence degree of E over F. Right. Second is that equality holds if and only if, and I will define what this means, E is separably generated over F. So what does E is separably generated over F? It means the following, that so let's put it down here. E separably generated over F means, this is a definition, means there exists a transcendence, there exists y1 through y L in E such that, let's call it yt, in such that, so if I attach this is a purely transcendental extension, meaning, okay, we'll say what this means. Let's review what this means. And this is separable algebraic. If you can find a set of elements which generate a purely transcendental extension over F, this could be empty, of course. In particular, E could be just a separable algebraic extension over F, and it would be called separably generated. Okay? This could be empty, possibly empty. So this must be a purely transcendental extension, and this must be a separable algebraic extension. That's the condition. Now observe that, do not jump to the conclusion that if I take some other transcendence basis, the same will be true. Need not be. Even for very good extensions, this is not true. For example, you could take, so what is important is there exists. Okay? Just to, I mean, this is so trivial that you will, all the same. So for example, I could take KT, this is my, or FT, this is my E in characteristic P, in positive characteristic. I could take, consider this, T to the P, right? That's a purely transcendental extension. Okay? But this is inseparable. Okay, that's an good example to keep in mind. Even for the best possible kind of extension, this is, it's, the thing is there exists. Okay. Okay, is the statement clear? So the point he is wanting to make is the following. So in fact, so before we prove it, I think more than the proof, what is important is what is he trying to do? It's not clear from the way he writes. There is no, I mean, we have to make our own, when you try to understand it, you have to make your own sort of roadmap, you know, markers on the road that he is taking you. So maybe if I say something, it might help you when you read the book. So I want to point out that he is going to make yet another definition of a separable extension. Okay, now I understand that that's already confusing the matter a whole lot, right? We have so many different notions of separability that it's a mess, right? Okay, now he is going to introduce yet another definition, and he is calling it separable. Okay, there is no comment at all. We should probably call it Springer separable. Okay, because it is yet another definition that he is making. The point is, it is going to coincide with the notion of separable algebraic, but that's a theorem. Okay, so finally they all match, but so he is going to make another definition. So I want to call it S separable for this is a what do you call it, provisional terminology, right? After you are done with the section, you can throw the provision out. So this is provisional. S for Springer. So he's giving this definition, which is equivalent to saying, although this does take a bit of work, we have defined separable algebra, right? We have defined separable algebra, namely that it is any algebra over a field, always the base is a field. If we call an algebra separable if when I base change to anywhere, any other field extension, the algebra is reduced. Okay. In particular, it must be reduced because I can base change to k itself, in which I get back a, and therefore reduced separable implies reduced is trivial. Okay. Now, what is a separable extension? Well, it's if a field extension is separable as an algebra over k, you call that a separable extension, right? This is one definition. Okay, this is Bourbaki's definition, and the definition he is going to give is equivalent to this definition. Okay, he is going to give a definition. I'm going to write it out. Although this may not be, this takes a little bit of work, but not a whole lot. Okay, for example, it is done in the notes. So his definition is the following: E is separable. So these are x. He is only doing it in this case, but you could do it more generally. Is separable. So in this case, meaning he is assuming that this notation, that E is finitely generated as an field over F, is separable if and only if, sorry, this is a definition, if given linearly independent elements x1, x2 of E over F x1 to the p, x2 to the p, okay, p is equal to characteristic of F, characteristic exponent of F. Let's be right. What this means is, if it is characteristic 0, then it is 1. If it's characteristic p, it is p. Okay. R or R linearly independent over F. So if I take a bunch of elements which are linearly independent over F, raise them to the power p, they continue to be linearly independent. This is the notion of separable. In this case, you call it separable. Okay. What I want to assure you is that, but maybe for the moment you should just accept it, is that this is the same as saying that E tensor L, that is the extension of E to L, is reduced for every L. Okay, that's what it means. Okay, and okay, this is the theorem. There is a proposition. So let me put down the numbers because you might. This is 4.2.9. Yes, they do. They do. That is for, see here we are not making any assumption about transcendence degree. This definition will hold for, see this definition there is, see normally when you define, you define in an initial, in beginning courses you define an algebraic extension is called separable if, right, that's the definition you have, right. So all of them coincide in the case, so if you have a finite extension then it is separably generated, implies separable, implies et al, all of these are equal. Okay, so it does coincide. Okay, now this one, so E is equal to F, so let me put this, E is separable implies, this is 4.2.10, E separably generated. This is the proposition, and just to so for the moment let's assume finitely generated field extension. For part of this it may not be necessary, but just for, then we are saying, we are giving, what is the content, what are we doing? We are saying we are defining a notion of separability for arbitrary field extensions, not arbitrary finitely generated field extensions, not necessarily algebraic. Right? These could be transcendental. Now, we have defined separability here. We have defined separably generated here, right? And now we are giving a criterion for when these are, and we are saying finally these things are going to be equal. They are going to be the same notion, and this is going to give us a criterion for that. This is a differential criterion, if you wish, for separability, namely that the dimension of this must equal the transcendence degree. This is clear. This is what we are doing, okay, at the end of the day. I repeat, so we are defining a notion of separability which coincides with your notion, as Gautam points out, that it coincides with the notion of separability that you know in the cases that you know. In fact, there are two of them. There is this separably generated, and there is this which is separable, and the point is that these two are the same, and also equivalent to saying that the module of differentials, universal module of differentials, has dimension equal to the transcendence degree. Okay? Okay. Now, so the proof is a bit I wouldn't call it hard. It's just putting inductions together, but it is particularly if it is for if you're seeing it for the first time, I would recommend extreme caution, in the sense of be very careful with it's you have to pay attention to detail. So now, in the light of this, let's look at the previous, so lemma 4.2.8, which we were doing last time. Let's look at that. I believe it will just be a special case of this. So let's write it out. Oh, is this okay? I erase this. So let's recall 4.2.8. This we did last time. I'm going to recall this. Recall. This is the case when E is generated by a single element. Then this part right, that is just this part. Okay. And the second statement we said was that we have equal to 0 if and only if E is separable algebraic over F. Okay, let's look at that in the light of this. Okay. Now, if the transcendence degree is 0, there is nothing to prove here. I am just trying to point out that 4.2.8 is just a rewording of this. Okay. So we are going to do this by induction, and we are going to refer to that. Okay. So it's important for us to recognize that as a special case of this. Okay. So transcendence degree is 1 or 0, right? So if it is 0, then this is trivial. If it is 1, what does it mean? That means X is transcendental. Greater than or equal to 0. See, if this were 0, this is a vacuous statement, right? Yeah. No, let's do it like this. Let's say we have proved that. I want to just observe that this is, I'm trying to prove this from that. Okay. Okay, we also have to, I'm claiming they are equivalent, but what is important for us is that this is implied by that. Okay. So let's try to do this. So I have to prove this. So if it is 0, then there is nothing to prove. If it is 1, what does it mean? The transcendence is 1, right? This is transcendental, that means, right? Which means this is non-zero, because this is if and only if it's separable algebraic. So it's not algebraic, therefore it's non-zero, therefore it must be 1. Okay, so this is in that case 1. Okay, right. And okay, now let's see if 2 holds. Well, equality holds means, well, if it is transcendental, let's see. So let's equality holds, and I can assume one of two cases, that this is 1. So I'm going to, let's prove this direction. So there are two cases when both are equal to 1 and both are equal to 0, right? If this is equal to 0, then it is just directly the statement, right? If this is equal to 1, that means the transcendence degree is 1, which means that this is a transcendental extension, and clearly that is separably generated, because you can take x, that itself is a purely transcendental extension. Okay. Now the other way, if E is separately generated over F, how can E be separately generated over F? There are two possibilities. One is X is transcendental, or X is algebraic separable, right? Okay. Now if X is transcendental, then again we see that these must be 1, both must be 1, right? This is 1 and this is 1 because it's less than or equal to 1 and it can't be 0, right? And if it is if it is algebraic separable, then both are 0, right? Okay. So it's a messed up version, meaning of that, and let's not worry about this is equivalent, but never mind, that's logically not even required. We have proved that, and therefore at least in the case when m equal to 1, this is proved also. That's what we just saw, right? Okay.
So we are assuming all definitions of separable are equivalent and then
No, not quite. No, that is later. This is proposition 4.2.10. Separable algebraic, and here also I have used separable algebraic. So I am using, okay, the one thing that I am going to use in the proof, that if you have a separable algebraic extension over a separable algebraic extension, that is going to be separable algebraic. Well, actually that is not, that's used only in that one, not even in this one. So at the okay, let's look at it. So what yeah, I understand what you're let's carefully think about what we are using. I have not used anything other than separable algebraic. Okay, you can take all that thing I said about et al, separable, etc. as extra material, which is not extracurricular. Okay, so is this? I'm assuming the notion of transcendence base degree, right? And here is my definition of separably generated, which only uses separable algebraic, and there is the statement. Okay, so we are not using, this comes later, as I said, that comes later. Right, Springer is not using, you use whatever notion you know about separable algebraic extension, and he is not using, and some facts about that perhaps are going to be used, but beyond that nothing is assumed. Okay, now let's say I'd say something about purely transcendent extension. Let's see what this means is the following, that if I, so very formally, I guess you know this, but let's just recall this. What does it mean to say something is purely transcendental? It's the following. So you have E is a field, right? You have an extension, and then you have elements f y1 through yt in E, right? And what does this mean? This means that it's the field generated by these elements, the subfield of E generated by F and these elements. That's what it means. Right. Okay. So you have, if I give you a bunch of elements, I can look at the ring inside E generated by those elements and also the field generated by those elements and E. Right. So let's not write. So that's, well, it's okay, that's correct. But let's this time I take a, yeah, that's why I got a little confused. I'll take a polynomial ring in those many variables, and so this is equal, and there is a map here, because from a polynomial ring you can arbitrarily specify the images of those variables, indeterminates. Okay. Now you call, I want to recall for you the notion of algebraic independence of these elements. A bunch of elements y1 through yt of a field extension E are called algebraically independent if this map is an injection. Right? This map is an injection. Okay. What that means is that if I take and so such a thing is called a purely transcendental extension. Okay. So in other words, what I am saying is a purely transcendental extension is one generated by algebraically independent elements. Right. So then this will become an isomorphism. No, there is not even, doesn't even exist. That doesn't even exist in general. Right? It's only if this is an injection does this exist. Right? Because you are inverting all elements. Right? Okay. So if this is an injection, you call these algebraically independent, and in which case the field generated by those is isomorphic to this field, and you call such an extension a purely transcendental extension. Okay. Okay. Now a transcendence basis is a purely transcendental extension over which the given field is algebraic. No, I didn't say that. A transcendence basis is a bunch of okay. You can define it in various ways. Is a maximal algebraically independent subset. Okay, and some elementary, or which may not be immediate in all cases, but some theorem will tell you that the maximal set has the same cardinality, independent of which it may be. You could have several different maximal sets a priori of different cardinality, but that doesn't happen. That you call the transcendence degree of this extension. Okay, and here it is bounded by M. Okay. Now let's start proving proving the theorem. Okay, looks given the time and how I am going, it looks like I will not be able to finish, but then I've already said that even, you please read it even if I don't get to the end of it. Okay, so I'm just looking, so I'll write this again when we come to it. Okay, I'll do some parts of the theorem and not others. So he's going to take D is equal to dimension of and does an induction on D. And he says we will prove all statements by induction on D at one shot. Okay, so if m equals 1, then we are done by 4.2.8, right? Okay, now let m be bigger than 1. Pardon me? D, induction on D, dimension of this. We have still not done the base case. We have still not done the case. No. Okay, let m be bigger than 1. So then, okay, so let's write down. So can I erase this part? So I'll write down, I'll use only, okay, okay, maybe I'll put it here. So recall we had this for this inclusion of extensions, we have right, because this, how do I get this? There is e to this, there is a e prime derivation. E prime derivation is definitely an f derivation, and so therefore by the universal property of this there is a map here, and then you have e prime over f, right, and once again this is by e prime to e is a algebra inclusion, and this is a derivation, f derivation. This is an f algebra inclusion, this is an f derivation. Therefore, by the universal property, so this combination, this composition is going to be an f derivation. Therefore, by the universal property of this, there is going to be a module map there. Now, this is an e module map. This is an e prime module map, and as we saw, since this is an e prime e module, I can, and this is an e prime module map, I can do this, and I have that I call the exact, that sequence is exact. Right. Another thing to keep in mind here is he's going to play around with this, and also what is going to be important is when is, so he calls this alpha, when is alpha injective? That is, when is that sequence exact with a 0 on that side, right? That is going to play a role. Okay. Now, right, so you should keep that in mind, that and the various definitions in mind, and he's going to play around with this. Okay, so I'm going to apply that exact sequence with that he calls, that is what he calls 15, with E prime equal to f x1. Okay, shows we have induction on D. We are in the case D equal to 0. Right, we are doing the case D equal to 0. So this is assumed to be 0. Right, so this is 0. That is so by induction on M, we may assume E is separably algebraic over fx1. So let's see, so we have E here, E prime here, f here, this is f of x1, this is E prime of x2 xm. Okay. Now by induction, so the number of okay, what induction is this? So by induction on M, so there is also an induction on M. Okay. So which statement are we proving now? I want to prove that, okay, what do I want to prove in this case? I want to prove that transcendence degree is 0, that is E is separable. I want to prove that E is separable over F, algebraic separable over F. This is what the statements amount to. If I put this equal to 0, right, then I am forced to show this is 0 and equality will hold. Therefore, I am forced to show E is separably generated over F, but its transcendence degree is 0. Therefore, it is E is. So what we are, so what I am assuming is that this is 0, and I am trying to prove that E is separable algebraic over F. Right? This is what we are trying to do. Huh? By induction now on M. So this is the case D equal to 0. The case M equal to 1 was 4.2.8, and for higher M, I'm doing it now. Right? This is the structure of the proof. Okay. Now, by induction, I know this is separable algebraic. That's by induction. Okay. This I know by well, do I know this? No. By using, okay. Okay, 4.2. Okay, I want to say that F. So what do I know that? Let's see. Right. So right. So we last time we saw here is okay, let's put this E separably algebraic over E prime implies alpha is injective. Okay, let's just quickly recall the proof of that. Okay, how did we do this? That we did by showing, so we want to say this is injective, which means that thing is exact. That is equivalent to showing after I harm that the resulting map that I get on derivations is onto. So what I have to show is that derivations, what I have is derivation given an E module, after I harm of E into that is derivations of f derivations of E into M. This is of course E with harm into this M is the same as E prime. So this is harm of E prime of this into M, but that's the same as that. Okay. So this is onto is what we have to check, if assuming E separably algebraic. Okay, and how did we do that? What do I have to show? That every E prime derivation can be extended to E, right? And it goes something like this. Okay, so just to recall the proof. So I'm given something here, I want to extend it here, right? So this is separable algebraic. So I choose sort of a maximal place. I mean, maybe last time we did it differently, but we can, you just look at a maximal possible place where there is an extent. You look at subfields of E, lifts, right, and do as on if it is required. Okay, do as on to make sure that there is a maximal one. Okay, and then you show that that maximal one has to be E, right? And how do you show that maximal one is E? Well, if it is something less, then take an element outside of that in E, write out its equation over it's separable algebraic. So you will get some equation. So this is okay, let's call it E. E is in E, right? Fe, right? So I'm claiming, so this is, let's say this is K, E belongs to E outside of K, let's say. Okay, and then Fe is F is in K, E is in Fe is 0, right? Okay. Now, so let's say F is equal to K0 plus K1, sorry for my notation, it might not be great, K2 T square, etc. Right? Okay. So what will you do with the D of, okay, F of T this is. So D of okay, I want to extend, of course I can extend this to see this derivation I can extend to KT, right, by arbitrarily telling you where T goes, but then to extend it to extend it to K adjoined E, right? K adjoined E, I have to make sure it is 0 on F of T, right? So how do we do that? So I take dk0 plus dk1t plus dk2t square plus dot dot dot. that's one part, plus you have an f prime t dt. Right? Okay. So now when I put x equal to t equal to, so let's see. Right. Yeah, so what do I, okay, this okay, this I should probably write not like this, but let me write it t like this, t square dk2 etc. Because okay, now I'm thinking of this, now t acts like x if you wish, I think like that. So this is going to be an element of M where t acts like x, right, and this becomes a f prime x d of x equal to 0. This is what I want. So, and I can do that, I can so the condition on dx will be, or de will be, sorry, de will be that de must be equal to minus of this thing dk0 plus e dk1 plus dot 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 divided by f prime of e. That formula will extend, right, that formula does extend the derivation to k, sorry, extend to k adjoint e, and therefore by maximality of k it must be equal to e. Okay, that's the proof. Okay, okay, where were we? So right, E is separably algebraic by induction, therefore this is an injection, right. Sorry, sorry, I didn't follow what you said.
Then omega u over f will be 0.
E prime over f is 0, yes. And then by the first case, we know that E prime over f is separable algebraic, and separable algebraic, okay, yeah, correct, indeed, exactly, yeah. So you conclude from this that by induction you know the hypothesis of this, therefore you know this conclusion, therefore you go here and conclude that this is 0, and then you use this, say this is 0 with E prime, so E prime is separable algebraic over f, so you get this is separable algebraic. So this is by induction, this is by 4.2.7 and 4.2.8 and 15, right. Let's see if that logic is correct. So by 15, sorry, first 4.2.7, since this is separable algebraic, it shows 15 is alpha and 15 is injective. Therefore, by 15, since this is 0, and therefore 4.2.8, this is separable algebraic, and therefore that is separable algebraic. Okay. Yes.
It's a separable algebraic and Transcendence degree is 0.
Yes.
And it is finally generated.
Yes.
So wouldn't it be just separate? Can't we use the primitive element theorem to directly say that And the proof we used last time to say that instead of the John's lemma and maximality which you use, it will be a finite extension, right?
Okay. So no, I was just doing it this part in general maybe.
Without the finiteness, the proof will be able. I mean, this is for any separable extension.
And
This is for any separable algebraic extension, yes.
4.2.7 is proof for finite dimensional E and E prime finite dimensional over there. Then alpha is in there.
Even if it
No, my proof here is arbitrary.
No, we use 4.2.7 to claim that alpha is injected.
Correct. But the proof that I gave here, just here,
Yeah.
of alpha is injective is independent of. Yeah, so see, he is making, see, it's a little bit silly in the reason he is assuming that two extensions of finite type at the beginning of 4.2.6 is unnecessary. It's not nice because it's true in general. He just wants to dualize with not M but E, E in place of M. I mean, that's right. So I think that is we can. In any case, I mean, if you prefer that, that's fine. Fine, I have no problem. Right. Okay. Now let's go to the case. So that does finish the case d equals 0. Okay. Now let's go to the case d bigger than 0. Okay. So can I erase that? So, no. I'll wait. So maybe we can erase this part. Yeah. Okay, so let's do the case d bigger than 0. Okay, assume that 1 and 2 are known for smaller values. I can do that because for d equal to 0 I've done both. Okay, the assumption is the whole bunch is pushed under the induction. Okay. By what we have already proved, there exists there exists x in E such that d E of f x is non-zero. D is bigger than 0, so the universal module is non-zero. It is generated by images of elements of E. Therefore, since it's non-zero, there is a non-zero element. That's all he is saying. Okay. Okay. So what you are using here is that the universal module of derivations is generated as an E module by images of elements of E under D. Okay. Again, we put E prime. E prime is equal to f of x. Put E prime is equal to f of x. And he is going to use 15. Okay. Now, what is the point? The point is, look here, this is x here, dx is non-zero here, but dx is going to be 0 here, right? The choice. See, x is going to come into E prime, so dx is going to be 0 here, but not here, right? So you have in this, there is a non-zero kernel, right? Which means that dimension has gone now. Okay, so we know that omega fx f is not equal to 0. Right? There is a non-trivial kernel here by 15. E prime or fx, it's the same. Right? I am using exactness only here at this point, which is always true. There is something that goes to 0 here, which something non-zero here which goes to 0. Therefore, this ought to be non-zero. That's all we are saying. Okay. So that ought to be non-zero. Okay. What does that mean now? So by the now going back there, what does that mean? Can I say E separably this fx is separably generated over f? Okay, he is going to say it differently. Okay, let's just okay. We conclude that. Okay, so what is dimension of what is this? It's non-zero, it is bounded by 1, therefore it's equal to 1, right? Right? Now, that means that alpha is injective. See, this is one dimensional, and there is a dx here which is non-zero, right? There was this dx belongs to E prime, and the image of dx here is non-zero. Therefore, here, what am I saying? That map has to be injective, right? So all I have to show is some non-zero element which is going to non-zero. Such an element is x, I mean dx, right? Therefore, it is 1. Okay. What is our conclusion therefore? So alpha is injective. Consequently, okay, so alpha is injective, so I have dimension of, this is my d, right? This is equal to this plus 1. So you have gone down by 1. So by induction, what do we know? This is bigger than or equal to this with the previous one, right? So this is bigger than or equal to the transcendence degree of, this is induction. Okay, transcendence degree of E over fx plus 1. Right? This is bigger than or equal to this by induction, and the plus 1 just comes along for the ride. But this is bigger than or equal to transcendence degree of E over F, because this is generated by a single element. So this is bigger than or equal to transcendence degree of E over F. Is that all right? Okay, so what have we done? We have proved 1, right? Okay, now let's prove 2. What does that mean? That means equality holds here, right, from this end to this end, which means in particular equality holds here, right, which means what? That this is E is separably generated over E prime, right, exactly. E is separably generated over E prime. Let's see, I want to show that, well,
And the second equality, for second equality to occur, x must be transcendental over f. So there are two inequalities there.
and for the second equality to occur, very good, yes, absolutely, x is transcendental over f. There you go, there you go, right. So to repeat, so this equality, so the fact that these two are equal implies two things, as Gautam correctly says. One is this, and the other is this. This is an equality. But for this to be an equality, x must be transcendental over f. Okay, so and by induction, I know if these two are equal, there is a transcendence. So I think it's called a separating transcendence basis. Such a basis is called a separating transcendence basis. So there exists a separating transcendence basis for E over E prime. I attach x to it, and I get a separating transcendence basis for E over F. Okay, are we done? Not quite. So the other way, right? Okay, so if E is separably generated over F, okay, I have to prove that equality holds. Okay, let's see. Okay, this is right. Okay, maybe we'll do this implication in general, right? I want to prove this implication in general. Okay, it's good to maybe separate it out of the. It has nothing to do with any argument. To just prove it in general that if so, then the equality holds. Okay, how do you do this? Okay, you apply that 15 with E prime equal to that purely transcendental extension. Right? I want to prove this one, right? For which, so forget, I mean, don't think of this as part of the, let's do this separately and imagine having done this before even starting on the proof of this. Okay. So I want to apply 15 with E prime equal to this, right? Now I apply that, but what do I know? I know E is separable algebraic over E prime. So alpha is injective, that I know. So this is actually an exact sequence. Okay, and then what do I know? What do I know about this? This is a purely transcendental extension. Okay, so this is a free module with T generators, right? I mean, it's a this I know is 0. Well, let's see. That separable algebraic, yes. 0, right? Yeah, that we proved that, right? Well, that's part of this. That's part of this, if you wish. Okay, I mean, you can say we proved it. Of course, we did, but it's this, right? So, so by 4.2.7 and 4.2.8, once again, by 4.2.7, I know that this is an injection. By 4.2.8, I know that this is an isomorphism, and I know the structure of this because that is just a purely transcendental extension. Correct? That's free. Yeah. So that does the theorem. Okay, I will just on just a little bit over time, not too much. Okay, like I said, 4.2.10, I haven't done it again. It's a very it's a bit of a subtle induction. Okay, so do read the proof. And so it's the statement that separably generated, or rather separable implies separably generated, and the other one is converse is also true, but that's an exercise. Okay, so 4.2.10 is towards consolidating the notion of separability and saying this notion of separably generated is nothing but is the same thing as separable, after you make that definition that we did. Okay, and please do also the exercises. Let me see, I noticed one typo somewhere, but not a very serious one. Let me see if in this book. Yes, there continues to be this typo in this book. Okay, so we meet on Friday. Yeah? So I'll start with, so please do ask questions, and I also assign the exercises at the end of the chapter, at the end of this section. Okay, so they are interesting exercises. You should, for example, when is something algebraic or not algebraic in terms of the image of D? Right, that's a nice question, isn't it? If I take E is an extension of a field, I have this universal module of derivations. I take an element of E, look at its image, and I want to say something about E being algebraic or non-algebraic in terms of the image of E, right? So there are things like that, and the converse of 4.2.10. So it's a so do look at it, and I am willing to discuss it in class if you demand it. Okay, if you don't, I assume that you had no difficulty, and I'll go on. Right. So we'll start with simple points, that is the notion of smoothness. Simple point just means a smooth point, and we'll start with that next time.